he is from the University of Auckland, New Zealand, but before, the best thing for me, what he is known, this is that he is one of the quarter of the quartet who wrote rings which are nearly close to associative. Okay, in Russian this is Korzybski Ksitin, я не помню английский, I don't remember the English translation. So this is the Bible for Jordan algebras and Lie algebras for a generation of mathematicians. But now, of course, he changed or extend his interests, and now the talk is framing is secret sharing. So this is cryptography, please.
Thank you very much, Isbel, and I'm very pleased to deliver to Bulgarian audience this talk. So I always wanted to come to Bulgaria, but it didn't happen. So at least I will come to you now virtually. Okay, so this talk is joined with Ivo Desmet. This is a rather famous cryptographer, who is working now at the University of Dallas, and my PhD student, Song Bao. By the way, cryptography is only a little part of what I am doing. My interest in cryptography is not cryptography itself. I will tell you slightly later what exactly I am interested in relation to cryptography. Okay, so Shamir once in 1979 said that, listen guys, it's not safe to keep valuable information on just one server that can be compromised. And he suggested the following idea. Let's keep valuable information on several servers in such a way that intruder to each particular server will see gibberish and will not see real data. So in particular, what can you do? You can share your data between 3 people or 3 servers in such a way. Look at this little picture. Here is Bitcoin wallet, and you have a key from your Bitcoin wallet, and you can keep it in parts of it in 3 different locations, or give it to share between 3 different people in such a way that any 2 of them will have a complete key, but not a single person here will have the whole key. Well, you might have heard that in former USSR, top 3 officials, Prime Minister, Minister of Defense, and the President had nuclear briefcases carried after them. And 2 of them were needed to launch a nuclear warhead, but not a single of them could do that. So this is what Shamir suggested. He suggested K out of N scheme based on Lagrange interpolation, and I will outline it further. So a secret sharing scheme divides the secret S in 2 shares, one for each user, in such a way that a secret can be easily constructed by an authorized coalition of users, but an unauthorized coalition of users cannot determine S, and preferably will have no clue about S. A secret sharing scheme has the following main ingredients: the access structure to the secret, mechanism of generating the shares, and secret recovery algorithm. For any authorized coalition, it is supposed to recover the secret if need be. Now, a modern view of secret sharing is that it is implementation of a certain power sharing agreement in organization or in society with respect to certain activity. For example, opening a safe in the bank. Each morning, employees come to the bank, and then a safe with cash has to be opened, and 3 of them swipe their cards. And if at least one of them was departmental manager, then safe will open, and if not, the safe will remain closed. Launching a nuclear warhead, as I said, in the former USSR, and the more important, signing a message on behalf of a large organization. I will dwell on this later. Now, the power structure is given by the set of authorized coalitions, those coalitions who are authorized to launch the activity by recovering the secret and using it. And at the center of implementation is this secret. But the secret is usually a string of zeros and ones. This string allows you to launch certain activity, but it may not have intrinsic value in itself. Now, let me give you the following example. So cryptographic algorithms are wonderful and they work well, but if people are involved, then everything can go wrong. For example, there is a simple cryptographic solution for 2 out of 2 scheme. Now there are 2 people and both of them are authorized to do something, to access their Bitcoin wallet, for example. So the cryptographic solution is very simple. The dealer, it can be any group or a field, the dealer shares the secret S by giving to participants elements A and S minus A. So if they get together, then just they add their shares and they will know the secret. Very simple cryptographic solution. However, okay, and by the way, the famous guys, Winklevoss twins, who were the first Bitcoin billionaires, manage their Bitcoin wallets this way. However, if they lose trust in each other, they are twins, brothers, they trust each other absolutely. But if they were not trusting to each other, then opening their wallet will become a prisoner's dilemma. Imagine yourself that 2 people are sitting one opposite each other, and they have to show to each other their shares. So if I open my share and show it to the other guy, then he will not have to open his share and show it to me because he will know the secret already. So in this particular game, the dominant strategy will be not to disclose. So that's a typical prisoner's dilemma. So a perfect cryptographic algorithm, but it does not work if people who are not trusting each other must be involved. Right, and that's what I am interested in. Cryptographic algorithm, because I was in economics for a while, so I came from economics, and in economics manipulation is very prominent topic. And so I'm looking at cryptographic algorithms from the point of view, and what if people will have to implement this algorithm with their own utility functions. And in this case, they will be tempted to manipulate in economics language, or it means that not follow algorithms in computer science language. Now, so in this paper, we are looking at digital forensic aspects of secret sharing. Since this manipulation is possible, that sometimes investigation is needed to establish, for example, who made a suspicious transaction with Bitcoins, who signed an offensive letter on behalf of organization, who opened the vault in the bank at 5:47 a.m. and so on. And in particular, in secret sharing, secret sharing is a clever, very clever set of algorithms, but it is very vulnerable because people can frame each other. So, and that's what we are investigating, the problem when, which occurs when a coalition is able to calculate the share of a participant who does not belong to this coalition. Then all kinds of things are possible. Then they can publish this share, blaming that guy, they can bribe, they can extort, and so on and so on. In extreme case, one authorized coalition can calculate shares of another authorized coalition and use the secret in some way and blaming another coalition for their action. Well, another thing that participants may have different status. Some may be more important than others, and access structure is a tool to reflect that. So let's define access structure formally. So this is, in economics terms, this is just a simple game. So you have a set of participants, 1, 2, up to n, and participant 0 is a dealer who is organizing the whole thing, manages the scheme. And access structure formally, this is a pair set of participants and a set of subsets. And this set of subsets satisfies the following monotonicity condition. If X belongs to W, well, W is winning in a simple game. That's the same terminology. If X is in W and Y is larger, then Y is also in W. Which means if X is authorized and can learn the secret, then larger coalition will be able to learn the secret as well. So monotonicity condition is very natural. Okay, so, and the set of unauthorized coalition is denoted by L usually. Okay, well, examples of access structures, K out of N structure. Well, that was the first access structure suggested by Shamir, that if coalition is large enough, has K or more participants, it is authorized. Well, weighted threshold structure, that's more kind of popular in economics. So there is a weighted, the weighting function, and every player or every participant get a weight, which is non-negative integer. And there is also a real number quota, Q. And X is authorized if combined weight of their weights is at least the quota. And this such a simple game or access structure is denoted by, say, quota, and then you list all the weights of participants. Now, computer science favors another type of access structures, which is totally, for some reason, economics totally avoids them. Suppose that we have partition of P into two subsets, non-intersecting subsets with N1 and N2 participants in each of them. And we assume that participants in each set are interchangeable. And if a coalition X, then Xi, that is part of X that falls into Pi. Now, Simmons in 1990 suggested the following access structure, which is called hierarchical disjunctive scheme. There are two thresholds now, not one. K2 is larger than K1, and coalition is authorized if it has at least K1 senior members. I will call P1 senior and P2 junior. At least K1 senior people in a coalition, or if not, then K2 people in total. Okay, so this is or, and that's why it is disjunctive, but if you replace it with and, then you have conjunctive schemes, and they were introduced only in 2007 by Israeli guy named Tassa. So in this scheme, again, you have two thresholds. One is larger than another, and coalition is authorized if you have at least K1 senior people and K2 in total. Not to be too academic, well, just let's see the following example. United Nations Security Council has 15 members, 5 permanent, P1, 10 non-permanent, 2 P2, and the passage requires approval of at least 9 countries, subject to a veto by any one of the permanent members. It means that we have P1 5 members and P2 10 members, and it is a conjunctive hierarchical scheme because all 5 permanent members must vote and 9 in total. By the way, it is also weighted access structure, and quota must be chosen 39, and permanent members should have weight 7, non-permanent should have weight 1. If all 5 permanent members vote, then that's weight 35. They need 4 other members to join them. And if only 4 of them vote, that's 28 plus 10, that's 38, still not enough. Okay, so let's look at the threshold access structure or K out of N structure. And what is actually Shamir suggested? Well, let's take a sufficiently large finite field, and that will be the domain of secrets and also domain of shares. And let's choose a distinct fixed number, non-zero elements of F, and make them public knowledge. Sometimes it's just 1, 2, up to N. And what does the secret do? Suppose S is a secret that he has chosen to share. He creates a polynomial. The constant term, T naught, he takes the secret, and then he generates also K minus 1 junk elements of the field and forms a polynomial. Here in this polynomial, T naught is meaningful, that's a secret, and other coefficients are junk, just to hide the secret. And then she gives a share as I, which is P of AI, to agent I. So every agent gets 1 value of this polynomial. And of course, if K of them get together, They will use Lagrange interpolation or solve a system of linear equations, and they will find this polynomial, and they will find constant term, and will discover the secret. However, if less than k people will get together, then under these conditions, T naught can be arbitrary. So the scheme is secure. Here is a pictorial interpretation of 3 out of 4 scheme. Since we have k equals to 3, we have to create polynomial of degree 2. C is a secret, and we give f of 1, f of 2, f of 3, f of 4. And then if 3 of them get together, they will learn the quadratic, and in particular C. Okay.
By the way,
Yes.
I believe you should never share the value of P of 0.
Oh yes, because P of 0 belongs to user 0, which is the dealer.
Okay. Yeah.
Oh, yes, that's what I just said, that if you have k values of the polynomial, then you can use Lagrange interpolation and reconstruct it. However, authorized coalition can reconstruct the whole polynomial. And since A1, A2, AN are publicly known, they can also calculate the shares of other users, right? So they can frame anybody. This makes forensic investigation impossible. Okay, so beautiful scheme, but such a huge disadvantage. Now, a slightly more general scheme is called linear. Error correcting codes, people will recognize some familiar things here. Suppose that we have now n+1 matrix with n+1 rows and with k columns. And the rows are H0, H1, Hn, and every participant, roughly speaking, gets a row. Now, given this matrix, what is the related access structure? The related access structure, sorry, users I1, I2, Ik will be authorized if their respective rows can span H0. And H0 is the row of the dealer. Now, how shares are generated? So this is more or less similar idea. So dealer takes T0, which will become S0, and k plus 1 random values, and just multiplies H by this column of these random values, and she obtains the column of the share S0, and secret S0, and shares S1, S2, Sn are given to people 1 to n. Okay, so how is the secret reconstructed? So if this coalition is authorized, this means that it can span H0, and then S0 will be obtained from their shares using exactly the same coefficients. You can look at this and see that if rows of H are linearly dependent with some coefficients, then SIs will be linearly dependent exactly with the same coefficients. One lesson from here is that secret recovery function is linear for every authorized coalition. Now, can framing occur in this situation? Well, if Hj, if these guys can also express Hj, then they will can be able to learn Sj, share of this guy. But spanning H0 and spanning Hj is different things. So they can span H0, but not Hj, right? So there is a hope here. By the way, Shamir scheme can be obtained by using this matrix, very familiar matrix. It's van der Monde ideas and so on and so on. So any k rows are linearly independent and they span dealer's row, and respective shares will span S0 similar. So Shamir scheme is a partial case of a linear scheme. Now, I promised to say this is a very important application of secret sharing, how RSA cryptosystem is used in large organizations. So I hope everybody now learns RSA in the university at about stage 2. The public key of an organization is N and E, and the private key or secret key is D, which is inverse of E mod phi of N, where phi is an Euler function. N is, of course, specially created. It's a product of two large primes. It's not important here. So encoding cryptotext is obtained from plain text by taking it to the power of E mod N, and it decrypted by taking C to the power of D mod N. Now, but that's also simple, but however, D, now if we have an organization, that secret key D cannot be trusted to any particular individual. Because, as I said, this D is also used, it's also used for decrypting incoming messages, but it's also used for signing outgoing messages. Digital signatures are very important in this world, and each time when you get your computer gets some update from Adobe or Microsoft, your computer checks digital signature of that organization. Now, to sign a message M, organization firstly applies hash function to M to make it shorter, and then take it to the power of D mod N. So this decryption exponent or private key is crucial to signing digitally messages, outgoing messages of organization. So it is reasonable to share it between people, but how can we do that? Now, if if the recovery functions are linear, there is a nice way of doing that. So what you do, you just share D between people, for example, using K out of N scheme, and then secret recovery function is linear, and suppose that M is a message to sign. Then what people can do, they take a hash of this message and take it to d of ij, so that they take it to the power of their share, not to the power of decryption key, but the share of decryption key. And then the trusted combiner can combine all these together, taking product of what he obtained from users. And the nice feature of that is that the message is signed, but decryption key was used but never revealed. So it's a very clever system. So decryption key can be used again and again because at no time it is ever revealed. Okay, so let me slightly move towards my personal results. So in 1956, Isbel, in the game theory setting, formalized the notion of importance of a participant in a game. So intuitively we feel that say permanent members are more important than non-permanent members. But how do we formalize it? So according to Isbel, P is at least as important as Q if whenever coalition X is authorized with Q, it is also authorized with P for any X which not includes P and Q. Okay, so P, what it means that P is at least as powerful as Q in relation to gamma. And of course, they are equivalent if P is at least as powerful as Q and Q is at least as powerful as P. Okay, my screen gets larger and I don't know what happens to it. Okay. Now, say, let's look at this linear scheme. So linear scheme can represent access structures that are not K out of N. For example, if you look at these matrix, then H1 and H2 can span H0. So users 1 and 2 are authorized. And then it's easy to check calculating determinants. Then any three other participants also authorized because the determinant will be non-zero. So, and any three rows, not including these ones, 3 of these or 1 these and 2 of these, they will be authorized. So any three, P1 and P2 or any three. So this is a disjunctive hierarchical with K equals to 2, 3 and N is equal to 2, 3 as well. So here P1 is equivalent to P2, but they are more senior than P3, P4, and P5, which are equivalent. Now, access structure is called hierarchical if the seniority relation is a non-strict linear order. For any two participants, you can always say if one of them is at least as senior as another. And this relation has no cycles. That's usually the case in any organization. And this concept generalizes notion of disjunctive hierarchical and conjunctive hierarchical. Now, a secret sharing scheme is called secure if non-authorized coalition can get no information about the secret, like in Shamir's scheme. it was proved in 1983 by 3 authors that for a secure scheme, you cannot have shares shorter than the secret in bits, of course. The length of any share in bits must be at least the length of the secret. And if we combine 2 requirements, first, if the scheme is secure, and then the length of any share in bits is the same as length of the secret, for example, all of them are from the same finite field, such schemes are called ideal. A Shamir scheme is ideal, and linear schemes are ideal too. And there is a very important connection of ideal schemes with matroids. So matroid is, of course, well-known combinatorial structure. Matroid now we have on 0, 1 up to n. And P prime is a set. I is a set of independent subsets. And the circuit in the matroid is a minimal dependent subset of participants, which is dependent, but any proper subset is already independent. And given a matroid M, we can define an access structure on P, not on P prime, but on P, in such a way that I1, IK are authorized if 0 plus I1, I2, IK is a circuit in the matroid M. Seymour in 1975 called this matroid port and provided, by the way, forbidden minor characterization for them. And one of the most important results in secret sharing is proved by Brickel and Davenport in 1991 that every secret sharing scheme defines a matroid. Every ideal secret sharing scheme defines a matroid, and its access structure is a port of that matroid. Unfortunately, it doesn't work in the other direction. Seymour showed that no matroid port of Obama's matroid can be an access structure of ideal secret sharing scheme. So there are matroids and secret sharing matroids. Okay, well, this is the main theorem which relies on technique is fully relies on manipulation with matroids, and that's why I will give you only the formulation. Now, what it says, that suppose that we have an access structure of an ideal secret sharing scheme, and we have an authorized coalition X in it. And we have a user B in this coalition, which is pivotal, such that without it, X is not authorized. And then we claim that X can frame any user who is at least as senior as B, right? So that is the main result of this paper. So let's see what consequences we have from that. One of the main results. In light of this theorem, for example, if B is a junior, the most junior member of this coalition, then X can frame any other who is more senior or at least as senior as B. But we were tempted to hypothesize that if there is a user who is more junior than anybody in the coalition, authorized coalition, then this guy cannot be framed. But it appears to be not exactly true, but we need to formulate it a little bit. Here's an example. So you have a linear secret sharing scheme over Z3, and you see that these two rows are linearly dependent. Right, and so what any pair of participants but P3, P4 can span H naught, and therefore any pair but this one is an authorized coalition. And we have P1, P2, which is more senior, and P3, P4, which are less senior. But however, P1 can frame P2 because H3 is H1 plus H2, and H4 is 2H1 plus 2H2. So this hypothesis appears to be not true, but to make it true, we need to specify better what authorized coalition should be. Okay, so if we have a hierarchical access structure, then replacing a senior member with a junior member, we say to be a shift of X. We take P from X and give it Q, which is junior. An authorized coalition is said to be shift minimal if it authorized, of course, then any subset is not authorized, and any shift of it is not authorized either. And shift minimal coalitions play a very important role in game theory, and they also play important role here. Now, our hypothesis will be true. If we have a minimal authorized coalition in an ideal hierarchical secret sharing scheme, then this coalition is shift minimal if and only if it cannot frame anybody who is junior than anybody in X. So, for example, let's look at, to get a feel for this, let's return to this example. So we learned that P1, P2 is authorized, then P3, P4, P5 is also authorized, and the first coalition is more senior than the second coalition. But you see that these guys, junior guys, three junior guys, they can frame both senior members of this society because this is a Vandermonde determinant and it's non-zero. So these three rows are linearly independent. They can span H naught, and they also can span H1 and H2. However, not the other way around. So these two senior guys cannot frame these junior guys because they cannot span any of their rows. Okay, now we consider a frame-proof secret sharing, which we first have to define. Definitely, frame-proof secret sharing schemes cannot be ideal because ideality leads to framing. A secret sharing scheme is frame-proof if no coalition can calculate a single share of a participant outside this coalition better than random guessing. And firstly, we observe that K out of N scheme can be made secure. We just modify Shamir scheme. As in the Shamir scheme, we generate a random polynomial of degree k minus 1 and over a large finite field. And dealer chooses uniformly elements A1, A2, AN. They must be distinct. And then she calculates values f of naught, which is a secret, takes for herself. And then f of A1, f of A2, f of AN. And then, unlike Shamir scheme, where A1, AN were made public, this time she keeps them private and gives to user I the pair AI and f of AI. And then any coalition of k participants can learn the secret, but they will not know any shares of participants outside of their coalition because these AIs remain unknown to them, other than their own. Okay, so building on this previous lemma and modifying the classical construction by Ito, Saito, and Nishizaki, I don't want to dwell into this construction. We can construct access structure. For any access structure, there exists a secure Frameproof secret sharing scheme. Okay, so what are the conclusions? Unfortunately, this paper shows the possibility that a coalition of participants could frame others, blaming the innocent participant in the use of the secret. Well, framing is, we have to understand that framing is a price that we have to pay for using an ideal secret sharing scheme. Ideal secret sharing schemes are wonderful. They're optimal in many other respects. However, the drawback of an ideal scheme is possibility of framing. Now, we created just ad hoc a frame-proof secret sharing scheme. We just showed that it's theoretically possible. However, we didn't try in any way to make it more efficient, most efficient. And that's an interesting topic. So what would be kind of analogs of ideal secret sharing scheme in the frame-proof world? So this paper has just been published in IEEE Transactions of Information, Forensic and Security, with amazing impact factor, 6.4. So we are very pleased about it. And effectively, this is the end of my talk, and thank you very much again for your invitation and for attention.
Okay, we thank you very much for your talk. It was quite interesting, and also in a private message before, I wrote that the ideal talk should have two parts. One part is for everyone to get something, and the other part is for the experts. So the first part, I cited the Russian expression "lig best," which means liquidation of illegally, which was popular about 100 years ago. And I think that we all are happy with the first part, and also I hope that the experts, they are happy with the second part. Okay, thank you very much. Do you have any questions or comments?
Let me ask something. Arkadii, in your talk, you didn't say why correspondence between participants will be run. It is supposed that some secret kernels are used, not public kernels.
In what In which sense? So that the dealer, yes, indeed.
Will send by public kernel, or in the case when he sends some data by public kernel, he should think about defense.
Yes, of course, so that the dealer uses private channels to give
Private
to
channel.
distribute shares. Yes, that's true. But there is also a trusted combiner in some cases, and that, of course, users send to this trusted combiners their shares using some private channels. So, what's the question? You can ask. You can ask me in Russian.
Ну, эти схемы, они все-таки для симметричного шифрования, так сказать. Потому что приходится разделять по защищенным каналам даты, ну, данные.
Well,
не предусмотрено, но можно, конечно, в комплексе сделать и передавать данные каким-то образом защищенные. Можно это добавить, и будет паблик схема публичная, ну, асимметричная.
But we are not talking here about private public key cryptography. I just used this RSA example to show how secret sharing enters as a primitive into this RSA when RSA is used by large organization. But secret sharing is I don't know what you mean by symmetric case in secret sharing.
I don't think about the symmetric. If you use public kernel, it will be asymmetric.
Public channel for what?
Public channel for some data that are translated, not translated, but передаются вот в процессах, которые были описаны. Если использовать открытые каналы, нужно заботиться о том, чтобы они были защищены, эти данные как-то. Но это можно сделать тоже отдельно.
Well, yes, but we are talking about secret sharing in its pure form, that how to protect channels, that's a separate issue, maybe, huh? No?
Yeah, I understand. Я только уточнял, что имеется в виду. Ну, а эту статью, она открытая, можно ее достать и почитать?
Она, безусловно, открытая, но если там вдруг начнут с тебя деньги требовать, сейчас просто свистни, я пришлю.
Спасибо. Я так и сделаю. А я даже смотреть не буду, я сразу свистну. А может, ты понял, я уже свистнул.
Хорошо. Имейл пришли.
Some other questions or comments?
This is an interesting talk. This was interesting talk. I like it.
We all like it, I hope.
I hope you got an idea of what secret sharing is.
Usually secret sharing, I use this as an example to show that even the most useless part of mathematics is very useful, starting from the number theory. If I want to say something to the students or to some people who are not involved too much in this stuff.
No, without digital signatures, we would have no digital electronic commerce, for example, you could have no ability to get upgrades from Microsoft on your computer. That digital signatures are extremely important in the current digital world.
Electronic cards are possible only if you have digital signature. No other technology is known.
Can I ask something I wrote in the chat about the paper?
Yeah, sure.
Yes, but I cannot download it and read it free.
Just send me an email and I will reply with the text of the paper.
Okay.
Before I try to find this using some pirate sites. Okay, maybe we stop recording.